Good day, everyone. This is the new topic for engine mechanics 2, which will be talking about cylindrical components under curvilinear motion. So for the cylindrical components, for its introduction, sometimes the motion of the particle is constrained on a path that is actually best described using cylindrical coordinates. So the difference on the topic of what we discussed last time about normal and tangential components. For the normal and tangential components, if the path is given, it's better that you solve a problem describing its normal and tangential. But if it is constrained on a path, that is actually best described using cylindrical coordinates. If motion is restricted to the plane, then polar coordinates are used. When we say polar coordinates, the location of the particle can be specified using a radial coordinate r, which extends outward from the fixed origin O to the particle. And also, the other coordinate is the transverse coordinate or theta, which is the counterclockwise angle between a fixed reference line and the r-axis. The positive directions of the r and theta coordinates are defined um, by the unit vectors ur and u theta. Here, ur is in the direction of increasing r when theta is held fixed, and u theta is in a direction of increasing theta when r is held fixed. And note that these directions are perpendicular to one another. So for us to visualize the polar coordinates, let's have this position. So at any instant, the position of the particle is defined by the position vector. So this is our position vector. And this is the figure. So here is our particle that is moving along a curved path, and it is described using polar coordinates. And the polar coordinates, these are the radial coordinate, which extends outward from the fixed origin O to the particle. So this is the radial coordinate. And the transverse coordinate, which is denoted with the angle theta, which is the counterclockwise angle between a fixed reference line and our axis. So this is our fixed reference line. And from the fixed reference line going to the r-axis, that would be your transverse coordinate or the angle theta. So for the velocity can be written in component form as the following. So this is the vector form of our velocity using the polar coordinates. So the VR and the V theta are the polar coordinates or polar components of your velocity, which is equivalent to the following. So VR is equal to the r dot, and v theta is equal to r times theta dot. So the radial component VR is a measure of the rate of increase or decrease in the length of the radial coordinate, whereas the transverse component v theta can be interpreted as the rate of motion along the circumference of a circle having a radius r. So in particular, the term theta dot, which is the derivative of the transverse coordinate or the angle theta with respect to t, is called the angular velocity, since it indicates the time rate of change of the angle theta. So common units used for this measurement are radians per second. So since the VR and the V theta are mutually perpendicular, the magnitude of velocity or speed is simply the positive value of using the Pythagorean theorem. So V is equal to the square root of, this is your radial component. So this is your radial component. And this one is your transverse component. And the direction of V is, of course, tangent to the curve. So as you can see here in the figure, the velocity here is always tangent to the curve path, which is the path of your particle. And for this, you can see here the radial component and the transverse component. On the other hand, for the acceleration, it can be written in the component form as the following. So this is the component or vector form of your acceleration. So this one is the radial component of your acceleration, and the other one is the transverse component for the acceleration. And these two components is equal to the following. So this is for your AR and for your A theta. So the term theta double dot, or the second derivative of the angle theta with respect to t, is called the angular acceleration, since it measures the change made in the angular velocity during an instant of time, and the units for this measurement are radians per second squared. So since AR and A theta are always perpendicular, and the magnitude of acceleration can be found simply using the following equation. So this is the positive value of this equation. So this is by using the Pythagorean theorem. So this one is your radial component of your acceleration, and the other one, or the other term, is the transverse component of your acceleration. And the direction is determined from the vector addition of its two components. And in general, like what I always mention, for curvilinear motion, the acceleration will not be tangent to the path, unlike or to compare with the velocity. So as you can see here, the acceleration of the particle is not tangent to the path. So here it shows its radial component and its transverse component of the particle. So speaking of cylindrical components, the equations that I've discussed earlier on the previous slides are for two-dimensional. If we encounter problems for three-dimensionals, we actually use cylindrical coordinates. So if the particle moves along a space curve, as shown in the figure here at the right side, then its location may be specified by the three cylindrical coordinates r, theta, and z. So the z coordinate is identical to that used for rectangular coordinates. So it is actually the height. And since the unit vector defining its direction, or the uz, is constant, the time derivative of this vector are zero, and therefore the position, velocity, and acceleration of the particle can be written in terms of its cylindrical coordinates as follows. So here are the component form, or the vector form, of the position, velocity, and acceleration of the particle using the cylindrical coordinates. And for the time derivatives, the previous equations required that we obtain the time derivatives of the r double dot, theta dot, and theta double dot in order to evaluate the r and theta components of the velocity and acceleration. So there are actually two types of problems generally occur. If If the polar coordinates are specified as time parametric equations, that is r is equal to the um, r, which is a function of time rather, or r is equal to rt, and theta as a function of time, which is theta is equal to theta t, then the time derivatives can be found directly. And if the time parametric equations are not given, then the path r, which is a function of theta, must be known. So using the chain rule of calculus, we can then find the relation between r dot and theta dot, and between r double dot and theta double dot. So just as an example, if you have an equation that is a time parametric equation for the angle theta, for you to determine the first and second derivative, we can determine its derivatives with respect to time directly. So the time derivatives can be found directly. So this first derivative will be 2, and the second derivative would be 0. On the other hand, if the time parametric equations are not given, and if especially the r is, the equation of the r is a function of theta, say r is equal to sine theta, so we can use the chain rule of calculus. So for the r dot, that would be cosine theta times theta dot. So that is the derivative of sine, which is the cosine, and the derivative of theta, which is the theta dot. And for the r double dot, or the second derivative, that is by using the product rule, since the two of these entities or terms are different. So by using the product rule, if u is equal to cosine theta, so the du is negative sine theta times theta dot. And for the v, that is theta dot, and dv would be, or the derivative of v would be the theta double dot. So using the product rule, which is udv, product rule is udv plus vdu. So that would be u is cosine theta, and dv is theta dot, plus v is theta dot times du is negative sine theta times theta dot. So you just only simplify this one to determine the second derivative of r. So that is the difference when you do time derivatives. So it could be a time parametric equation, or if the time parametric equations are not given, and the path and if the path, which is the r, is a function of theta, so you will use the chain rule of calculus, like what we did here. So just a procedure for analysis. The first thing is coordinate system. It's very important to establish the coordinate system. Polar coordinates are a suitable choice for solving problems when data regarding the angular motion of the radial coordinate r is given to describe the particle's motion. Also, some paths of motion can conveniently be described in terms of these coordinates. To use polar coordinates, the origin is established at a fixed point, and the radial line r is directed to the particle. And the transverse coordinate theta is measured from a fixed reference line to the radial line. For the velocity and acceleration, once r and the 4 time derivatives have been evaluated at the instant considered, their values can be substituted into the previous equations to obtain the radial and transverse components of velocity and acceleration. So if it is necessary to take the time derivatives of r, which is equal to a function of theta, then the chain rule of calculus must be used. So motion motion in 3 dimensions requires a very simple extension of the above procedure to include the z dot and z double dot, or the first and second derivative of the third coordinate, which is the z coordinate. So after this one, we'll have 3 example problems. The first 2 examples will focus on the 2 dimensionals, and for the third example, we'll focus on the 3 dimensionals. Take note, for 2 dimensional, that is by using polar coordinates. So that is r and theta only. And if it is a 3 dimensional, that is what we call cylindrical coordinates. So that would be r, theta, and z coordinates. So that is the difference between the two.